All right. Hello, everyone. So first update is that the rollers that we catted last week are all done. You can see the rest on the table behind me. Both crown rollers here and flat rollers are done. So hopefully they work. We'll find out tomorrow. Um, I don't know if we have the actual belts for them yet, but I've got some Velcro that's 3/4 inch wide that we can at least use to test, and it may actually just be good enough to use as our belt. So we've got that. Let's see, seems to be some confusion over the attendance policy. Um, so these Twitch meetings, these are VODs get posted to YouTube. These are watch them when you are able. There's, it's great if you're here and paying attention on time and contributing in chat and all that. Um, Otherwise, if you've got other commitments, you can watch them later. You still need to watch them because it's all information you need to know before, we hit it hard in build season. If we're trying to teach people, like tonight's topic, how, the basic pieces of the control system in the middle of the season, it's we're not going to have a very good time at competition. I can tell you that. Um, but the in-person meetings, we are taking attendance, and that is what counts towards your, a total attendance for the year. And if you recall the team manual, if you are under 50% attendance at the end of the first month, which would be you know November 1st is when that kicks in. So there's four in-person meetings between now and then. You miss three of our in-person meetings, by that rule you are off the team. Now we understand that we kind of rushed back to being a team in effort to push for Cowtown, and that people had, by virtue of us being so late out of the gate, people had joined other clubs. Um, if you have a situation where you are going to miss three of our in-person meetings, three or more, you need to email the robotics club email, robotics@smithfield.k12.mo.us, explain your situation, and we might be able to, you know, keep you on the team. What we'll probably do is ask you to fill out some grant applications to try to get the team some money. It's not really a punishment. It's a here's this alternate thing that you can do to have it be considered a meeting. You know, and we'd rather you be there and participating on stuff that we're trying to do to make the robot at least semi-competitive for Cowtown. But we understand that people have situations and other things that again we were late getting back into the groove as a team for this year, so we'll work with people there. Now, if you're not going to make an effort to do even explain your situation, then I guess if you're not attending meetings, you're off the team. I can't do anything for you there. But that is the current state with attendance and team expectations and all that. So on to, I guess, more of what we were actually trying to teach tonight. Intro to the control system, and this is the all team Twitch meeting. I'm sure the first question here is, why do the CAD and design people need to know about the control system? Well, you all are going to be troubleshooting it and plugging things in and wiring it up anyway, alongside the control system people. And also, you're more likely than not, there are going to be people on the drive team or messing with the robot at one time or another that aren't on the controls team. So you need to know like the basics of what the control system is and what all the components are and how do they get plugged in together. I'm not asking that you got, this presentation has zero code in it. We explain where our code gets run, but there's no coding involved. It's just here are the components. Here's how they, generally how they talk to each other, etc. So yeah, what does the control system do? It makes the robot not a paperweight. Control system doesn't work, the robot doesn't work. The battery's not plugged in and, the switch turned on before the match. Guess what? We're sitting there dead the whole match. Doesn't matter how good the, mechanisms and the machining is. The control system is bad. We're not going to have a good time. So why learn about it? There's relevant skills here. Even if you're a pure, mechanical engineer, you're probably going to use computers and stuff to design it. You might as well learn about some of these things and how to troubleshoot them. Have a functioning robot, exactly what I just explained with, it making the control system making the robot not a paperweight. Maybe even have a well-performing robot, which goes along with this next point. The more we can automate with a control system, like humans are actually actively terrible at driving our robots. They make mistakes, they choke, they, are inconsistent, they let emotion drive the situation. If we could get to the point where we could automate the entire match flow, we would do it because humans are just not good at doing robot things. So we're just gonna hit you with a map of the entire control system right off the bat. The boxes are different devices in the chain of control system, starting from, the driver pushing a button on a controller, going all the way down to moving a motor or a solenoid or turning on and off a compressor, any of that. So what I would recommend is if you've got the slide deck pulled up at home, I would just leave this up so that you know where we're at as we're going through the rest of the slides. So leave that up. We're going to start at the input device. So, the robot is driven by USB based controllers. Typically, we go with X input based controllers, whether it's, Xbox 360, Xbox One, Xbox One S, they're up to now, or One X, the Xbox family of controllers. Specifically, let me flip back to my face cam. Specifically, and I have another one of these at home, we use a controller that's a lot like this, and it's got a paddle set that goes into the back. This is a Power A Fusion Pro. It is an Xbox One compatible controller. And it's just got these little extra paddles on the back that we can remap to face buttons or the D-pad. That just allows the driver to be able to access those buttons while driving, because you to hit the A button you have to take your finger off the joystick. That's not what we want. We want the driver to be able to activate that function while they're moving if they want to. So, this $80 controller gives them the freedom to do that, and also allows them to, customize. This whole front panel comes off, and it's got other joysticks in the box. You can customize all that. So not to make this too much of a controller advertisement, but these controllers for the money are fairly nice. I found them like at Best Buy one night while we were actively competing at an event, and we had a controller that broke. So let me go back to PowerPoint. So you can see on the right, you can actually kind of see. Oh gosh, I accidentally hit the Xbox home button. You can actually see the window, and I can get it. Let me just go to display capture here. So never mind the driver station being up there, but USB game controllers. You can see that controller I was just showing is plugged in. If you go to properties, it actually shows, the joysticks, that thing that's moving around. Here's the other joystick moving around. The triggers are actually analog, and all the buttons are here in the field of view hat comes in. Now, if you go to USB, the controller's in the driver station, which, we're not there in the slideshow yet, but I'll just show this anyway while we're here. You can see where, even though that window is not updating, once I get into it, you can see how, the data that's down here on the driver station is actually what the coders look at, and it matches up pretty well as just a remapping of what Windows comes in. Now you can see the arrow between the game controller and the driver station is bidirectional here. Let me go back to the PowerPoint. It's bidirectional. If you notice in the screen capture window down here, there's a rumble here. Through code, we can actually make the joystick or the controller rumble based on certain action, whether we have a sensor to detect that, we actually picked up a game piece, whatever. We have the ability to alert the driver through a rumble about some situation on the robot. And we're not locked into using Xbox One controllers. We can actually make our own custom button boards, but again, generally it's going to be over USB. And also a note I want to make here is that if you are driving the robot and you notice things are activating when they shouldn't be, go pull up that window and make sure the controller is actually reading its inputs correctly. We actually had a situation at the 2020 only event that we attended where our shooter was triggering throughout the entire match because one of the triggers on our joystick broke. That's what led me to go buy a controller that looks like the one I had on the webcam a bit ago. So the driver station laptop has to be a Windows laptop to run that app that was to run this application. It has to be a Windows laptop. So it runs the FRC driver station app and any dashboards that we program. We use anymore. We just kind of use Shuffleboard, and there's stuff from our code that we actively program to show up here. I'm not connected to the robot, so none of the values and stuff are showing up here, but just know that we can see information from our robot on the laptop screen while we're driving it. So this the controller plugs into the laptop by USB, and then either via Wi-Fi or Ethernet, it talks to either the robot or the FMS. So the FMS is what we call the field electronics. FMS stands for Field Management System. And every robot gets their own IP subnet so that the robots can't talk to each other, but they can. Everything on the robot's network, including can talk to the robot. At home, we just bypass the FMS by just connecting straight to the robot for testing because we don't really have an FMS at home. Technically, we could make an approximation of an FMS, but we just don't. Control systems team people take note of, the whole subnet thing and the IPs involved. If you're CAD, don't really worry about this too much. CAD or design or, not programming, don't really worry about that. So the FMS, it enables all the robots at the same time. It disables them all at the same time. It makes sure that, the match happens and that all robots are connected, throughout the match, or at least it tries to. Sometimes you get disconnected on the field and it's not like you get a replay for that. And so sometimes that's a very annoying situation. So the FMS connects to the robot radio. There's a spec router that we're forced to use by rules. It either uses 2.4 gigahertz or 5 gigahertz Wi-Fi. At home, at the school, we use 5 gigahertz. There's a bandwidth cap, which means that we can't go crazy with a webcam stream going to the robot. We're usually limited to like maybe 480p resolution, which is like an old DVD. We can't go crazy with 1080p streams. It usually means that our vision processing has to take place on the robot because, we can't be sending that stream back and forth at super high resolutions. The radio, if we get in a heavy impact, it will reset. It takes like 30 seconds to reset. You want to try to, as much as possible, isolate the radio from taking heavy impacts because it doesn't like them. It gets powered by the Ethernet cable that plugs in. We've got a power over Ethernet injector that gives it power. Or you can use the barrel jack. I prefer PoE. If possible, you power it by both. But the barrel jack has a tendency to slip out, which is, given that this is the point of connection of your entire robot to the drivers, it has to work or else you're just going to lose the match, pretty much. Because you're not going to be moving if this fails in any way. So making sure that the radio is connected and in a spot where it's going to be reliable, and basically you want to put this radio in as good a situation as you can. You don't want, big metal structures around it to, put it in what's known as a Faraday cage and make it an unreliable connection to the field or the laptop. It needs to be high up, pretty exposed without being, open to big impacts. You really kind of have to baby this router to keep it running right. Roborio, the main computer on a robot. It is the code that we write, for the most part, runs on this. All actuator signals have to come from this. There's some explanation about it, but we can't just, have a Roborio on the robot, but then put like a Jetson on there or, Raspberry Pi directly connected to motors. We can have a Raspberry Pi that decides actually what the motor should do, but the Roborio has to be the one, sending that command. Think of it like the Roborio has to have veto power over every bit on the robot that actually moves. Because it has the safety code on it that when the robot's in a disabled state, it, stops things from moving, because that's a huge safety thing. For this year, they're coming out with a Roborio 2.0. We'd have to spend $485 to be able to get one of these. It's out of stock. Actually, I think just today, we have the option, and we might discuss it tomorrow at the meeting. We are given a basic drive base every year. We really need to take a look at our resources and see if we want to build a custom frame for the 2022 season. If we're building a custom drive base, then we need to opt out of the drive base kit that AndyMart gives us, and that gives us a like $450 voucher, which would make this a very cheap option to at least get one of them. The big difference here is it has more RAM. Our code is on an SD card. We can still deploy over Ethernet like we do today, but if it is possible to write code that's so bad that it basically bricks the Rio until you get that code off of there. In this case, switching out to a known good code would just be switching SD cards to, one that has known good code on it. So, Roborio plugs into the robot radio over Ethernet. There's just an Ethernet cable coming out of here, and it goes over to that radio. Motor controller and motor. There's a lot of options. We've got, brush motors over here. We've got a brushless motor within the Falcon 500 that has the motor controller and the motor just all together, all in one. And what we have a lot of is the Neos, which is a brushless motor and motor controller separated out. Motor controller communicates with the Roborio over CAN. It can use PWM, which is what servos use a lot for people familiar with those, or the Vex motors that you use in PLTW classes are all PWM. We use CAN because it allows us to use some advanced options. We can have some position control and among other things that run on the motor controller rather than the Roborio. The Roborio is very limited in how much processing power it has, at least the old one. I don't know how much we could get away with if we get a new one, but we're almost always pushing the limits of this guy. And so the motors are powered by the battery. Later there'll be a diagram of the electrical system, and I'll explain more about how much power we have available to us, etc. But the brushless motors are a lot more efficient than the brush motors, so if at all possible, we need to do some fundraising so we can use less of these and more of these. Pneumatic control module. So we can use pneumatics on the robot. CAN stands for Controller Area Network. PWM stands for Pulse Width Modulation. And PID stands for Proportional Integral Derivative Control. So CAN is very commonly used in like modern automobiles. They have a whole bunch of different like controllers for like your engine, the transmission, various body control modules for like the radio and, whether or not the door's open or not. And they actually talk over the same standard that we use to talk to different motor controllers on the robot. CAN is a red or green and yellow wire, just two wires, ideally twisted, that just gets daisy chained between every controller that is on the controller area network. PWM is pulse width modulation. It's a 3-pin connector, red, white, and black. If you'll see it on a lot of our older robots. It's just a 3-pin connection, and it actually plugs in over here on the Roborio. And then you wire power separately. Power is run separately from CAN on these motors and motor controllers. But communication with the Roborio is CAN or PWM. Pulse width modulation is it just modulates a wave to the motor controller to give it basically a percent output that it needs to try to hit. So, over PWM, all you can communicate is, I want this much power forward or backward. Over CAN, you can say, like, I want to go this fast, or I want to use this many volts, or hey, here's this many volts, but also I want to set an amperage limit. And then PID, proportional integral derivative control, is how you get that positional control, where you could just tell the motor controller, I want to go here. I'm not going to go too much into that because that gets into programmer stuff, but just know that it is a thing that we're doing. So pneumatic control module also talks over CAN. That you can actually see the green and yellow here, where you have two wires running in and two wires running out to daisy chain. And you can see it up here on our older control module that we have on the current robot. This just sends, like, you can see all these red and black wires. This just sends basically on or off to solenoids right here. And these solenoids just divert air to either this side or this side of the cylinder. If you send air here, the cylinder extends. If you send in air here, the cylinder retracts. So, pneumatic control is very simple. It's very easy for the programmers to use. We don't have to deal with positions. You put a pneumatics on an arm, it's either in or it's out. There's no ambiguity there. There's no tuning a PID. We just need a simple arm, and we don't need multi-position control. Pneumatics are a good way to get that. However, with pneumatics, we have to have the air compressor and air tanks to be able to use it. And a problem with pneumatics is they are very, very inefficient. The compressor is very good at making heat, not so much at making compressed air, despite it being an air compressor. The pneumatic control module handles giving the compressor power. There's just, somewhere on here, just a red and a black wire that go to the compressor. And the module handles turning it on or off based on, if there's enough pressure in the system. Because the pneumatic control module also has an input for a pressure sensor that gets put in our air system to detect if, we have a safe amount of air in the system. But yeah, the compressor pulls a lot of current. If you're running one of these, what you want to do is you want to charge up the entire air system, get it full, and then swap your battery before the match. Because you ideally don't want this running at all during the match. But, it almost never fails that it does. It just compresses air and stores it in the tanks to be used by the solenoids in the cylinders. Servos. They are position control over PWM, pulse width modulation. Instead of that modulated signal being for like a percentage output, it's like a position thing. FRC rules kind of regulate these things to be so weak that they're usually not useful, or at least we haven't in the past. Maybe we can find some opportunities to use them, and I actually think Mr. Uladol would probably be more knowledgeable than me about what these things can actually do, because personally the only experience I have with these is from way back in the day when the PLTW Vex kits were brand new, and that was when I was still a student. So, they're usually fairly weak. One advantage is we're limited on the this guy, the power distribution panel of how many motors we can run, and servos don't use one of those up. So if we have something that doesn't need like hardly any power to, move something, we should look into using these because it frees up motors for other things. Sensors. I'm not going to go too in depth here because there's like a million different sensors that we can use on the robot to, detect things. The big ones we use are encoders. They track rotation of a shaft. That's how our odometry works on our drive. It's how, our hood on the robot works. It's how so many other mechanisms that we've used in the past have run based on mostly just an encoder. They, a lot of them, there's just like a little wheel in there, and they've got a sensor that counts as like little things on it move past it. But yeah, just know that encoders can track how much a like shaft has rotated. Limit switch beam break, they just detect whether something's there or not and send. As far as the programmers are concerned, we get a 1 or a 0, or open circuit, closed circuit. They plug in. Usually those are digital, and so they plug into the DIOs over here on the Roborio. There's usually a power ground and a signal. You have to make sure you've got it wired up right. Gyro accelerometer, or IMU. We have a NavX that's a gyro and accelerometer. It tracks like angle and acceleration to where we can get like a pretty good like guess at how much the heading of the robot has changed since it started up in a match. Ours plugs into this thing in the middle, which has a whole bunch of different protocols in it. If we really want to get off in the weeds, we can explain that in person tomorrow. So power delivery on an FRC robot. So we get a battery. there is a white list of batteries in the manual that we're allowed to use. They're all about 17 amp hours, which equates to about maybe 7 usable because it's lead acid. And so the voltage droops. I mean, there are times where after a match, we're down to like 10 volts out of the battery. And there are 12-volt batteries standard. Usually, if you're pulling a battery off the charger to put in the robot, it should test at around 13.4 volts because almost every charger ever overcharges them. And then so yeah, and then there's a plug here that's not shown on this diagram. So the battery has a plug on it because they're hot swappable. Plug that into the breaker and the power distribution panel. The breaker has to be closed for this to get power. And this splits out power to, the Roborio on a circuit, the PCM or pneumatic control module, which further splits it out to the compressor and the pressure sensor. It powers our radio through the VRM, among other things. And then all our motors plug into these ports. And on the current power distribution panel, we're limited to, I think, 16 or 18 motors. One of the reasons I would like, again, we need to really do some fundraising, and why I'm trying to get the students who aren't here enough to not get kicked off the team to fill out grants, is there are new control system components, and there's a new power distribution panel that should be legal for next year that allows us 2 more motor slots. That'd be really nice because last 2 years we've been up against the limit of motor slots. But so realistically, out of the battery, you can get about 300 amps peak, 120 amps steady state. And our drivetrain alone can pull like 300 amps on its own. So efficiency of our mechanisms is very important. That's really what separates the good teams from the still pretty good, but not best teams. One of the things is that 120 amps is like 3 of these motors at once. So all the motors have breakers on them. Like the big connectors here are on 40 amps and the smaller ones are 30 amps. Another advantage of the new power distribution board is that every motor slot is a 40 amp slot, but you can very temporarily break that 40 amp limit. It's just, all the breakers on our robot are thermal, including this 120 amp breaker. And so you have to be pulling over the stated limit for a decent amount of time before it trips. And when a match is only, 2 minutes and 15 seconds, it really takes a while to trip that. Oh, and another thing you'll notice here is that there are different wire gauges that are mandated by the rules. Like from the battery, this has to be 6 gauge. We voluntarily upgrade to 4 gauge because wire gauges are actually backwards in number. Like 6 is actually thinner than 4. And so, these are mandated to be like 12 or 10, I think. And then this down here, I think, can be like 18 or 22. Check the rule book. There's a whole section in the rule book on what gauges of wires that we need. And you can see kind of a key up here as to what this has the mandated minimums. So, a number larger is legal. And they will catch that in inspection. And one year, I think it was 2017, we showed up with all kinds of illegal wire gauges and had to rewire our entire robot in the pit before we could go practice. Oh, that popped up a thing. Oh, and if you open the slide deck, there's a link to this so you can see it in better resolution. Pneumatic system. So this is not the power, but like where the air goes. So you have your compressor. It charges up an air tank. You are not limited to just one air tank. You can have as many as you want, but more air tanks means more weight and more work for the compressor to do to charge it up before the match. These compressors are only rated for a duty cycle of like 9%, which means like in an hour you can run like let me pull up a calculator. 0.09 times 60. You can have the compressor running for like 5.4 minutes out of an hour before you are exceeding the spec. At competitions, we are almost always exceeding the spec. Just a fact of life. So we burn out a lot of compressors. Um, Air tanks. They're in the in the design tool. We actually have a way to calculate how many air tanks we would need to not have the compressor turn on during the match. So we should be using that. Limit switch. That's that pressure switch I was talking about. This is required. It has to be plugged into the pneumatic control module to turn off and on the compressor. This trips around 120 psi. So this will charge the air tanks up to 120 psi before shutting the compressor off. Then there's an emergency air release valve. If for some reason this limit switch doesn't work and allows us to go over 120 pounds, which is what the air tanks are rated for, this will bleed off any air above 120 psi. And then for working pressure, we are regulated to 60 pounds. And so this will cut it down to 60 before it goes to solenoids. And we're free to have as many branches of regulators as we want if we want to try to conserve air by having a low pressure thing run it, even as low as like 5 psi. That is totally legal. So that's really all I had for y'all tonight. Kind of a short meeting, but that's fine as we're gonna have our in-person meeting tomorrow. I'll stick around for at least 5 minutes if anyone has any questions. Quick crud. Um, so I guess. So can anyone put in Twitch chat? Where does our code run on the robot? Yeah, very good. Um, here's a subjective one, which could have multiple good answers. What is a part of the robot that we should be very careful with and check before every match? There's a lot of good answers here, but I'm just. That is correct. Yes, we should check the battery before every match. What's another part of the control system we should check? The robot radio. That's a good one. You don't want to go out on the field with an unplugged Ethernet cable. But yeah, the battery, we need to check it, make sure it's at the right voltage. We should be switching out, have a fresh battery for every match. And yeah, so robot radio, that's another good one. Um, so what I would say is that I gave you all a trick question. The real answer is we should be checking all of it. You know, if you see loose wires, that's kind of a bad sign. If you see things that look obviously burnt, bad sign. But the robot radio and the battery are the two very common culprits of matches where a robot doesn't move or moves poorly or disconnects in the middle of it. I mean, when you're plugging in that battery, you need to make sure you get that connector in all the way. All the way. When you the breaker has like a flag on the side of it that you push in to turn the robot on, you need to make sure that gets in all the way. Not just barely enough to where it makes connection, makes the robot run. Because as soon as we get hit, that's going to come flying out, and we're going to sit there dead for the rest of the match. Um, That's one last question. What you have a mechanism, and you want to know how far it has moved in a direction. What sensor would you use for that? So, Bueller? Bueller? Encoder. Yes. You should use an encoder. Well, I guess that's all I've got. I Either you guys are um, looking it up in the PowerPoint, which some of those answers were so quick it wouldn't be just looking it up out of the PowerPoint. But um, I do have to thank you all for paying attention. So many times I give a presentation like this and it's in one year and out the other of the students. So thanks for showing up and paying attention, and see you all tomorrow. Peace.